So this is the topic for today, position-based dynamics. There are two, I would say, seminal papers on this topic. The first one is titled appropriately Position-Based Dynamics by Matthias Müller, and they were formerly with AGIA, but now they were acquired by NVIDIA. So position-based dynamics is part of what you might know as NVIDIA physics. So these guys are in games, so this technique was developed primarily for computer games, but it's equally important and equally frequently used in film, because this guy is really, I'm not happy with this resolution. Well, maybe the focus. More of this. The interesting thing is that when there is some new idea, usually it's not just one person who has that idea, but like it appears independently at multiple places. And this guy, Jostam from Autodesk, he had basically the same idea at about the same time, except that he published it a little bit later. Nevertheless, it's really the key idea is the same. And this, what he calls it nucleus, and it is part of Autodesk Maya. So if you are using Maya for simulating elastic or rigid objects, this is what you are probably interacting with. All right, so let me start. Matthias's paper, the position-based dynamics paper, a little bit easier to understand, and it also provides implementation details. So this is what we will mostly focus on today. So I want to start, as is a good habit, by showing you the video to give you some nice, cool motivation. So this is the original. So mind you, this was a 2006 paper, so it's now slightly old. And you will be amazed how simple it is to produce results like this when we discuss about the technique. They look pretty good. So this is some coupling of elastic, like cloth type things, like racks or something, with rigid bodies. And this, the claim of this is really accuracy is not the main point here. The point here is that it's simple, robust, and fast, useful for computer games. These qualities are exactly what you want in a computer game. Accuracy and like physical correctness, not so much. You will see in a little bit why. Nevertheless, you can do all sorts of cool effects. Here is an example of pressure, and you can combine all sorts of physical phenomena together. Yeah, you can tell it's from the game guys. They have some sense of humor. This one is even better. In one of his previous videos, there was a disclaimer that no yellow animals were harmed in making the video. I think that will be the next lecture. Yeah, so this is some skin character with a piece of cloth colliding with it. And now you probably have a little bit of appreciation of how tricky is it to get all these collisions right, and so it doesn't explode and so on. And it's really amazing how simple technique can deliver effects like this. Self-collisions with PBD, that's like an extra credit thing. Oh, PBD, I should have mentioned that. That might be even better motivation. It's also going to be the next homework after I'm done with Jello. And we will do a homework on PBD that turned out to be the most popular homework last year. And nobody, I think nobody tried to do the cloth self-collisions because they are really tricky. Actually, I think somebody tried, but nobody really got it to work reasonably well. And there is tearing also. You can update the simulations really quickly at runtime, which is also cool. Like computer games always like this. You can like destroy the scene, rip it apart. Yeah, the parameters are perhaps one of the weaknesses of PBD. Of course, you can adjust parameters. You usually have more parameters than you would wish for. That's the case here too. Did we give you some parameters for the Jello cube? I can't remember right now. Or do you have to tweak it by yourselves? Huh? You got some parameters? But yeah, Both is true, right? And by the way, mind you, this is all in real time, I believe, and that was on relatively older hardware. So you can see, like, yeah, it's not the most amazing physically based simulation I've ever seen, but given that this really runs on like computer like this, would run no problem on my MacBook. All right, so that was the video. And now I need to explain you how it actually works. So let's do that. So by now you are experts, or almost experts, on the classical methods for simulating dynamics, right? I already been talking about them quite a lot, so I will just, it's pretty annoying, this schedule, isn't it? At least zoom it to make it a little bit. Oh, shit. That's not what I want. The wrong button, sorry. I meant this button. Okay. So the classical way to simulating dynamics is to write down Newton's equations of motion, right? Which they involve some forces, some accelerations, and the Newton's second law is the relationship between forces and accelerations via masses. And then we need to solve the integration problem, the time discretization, and we can either do implicit time integration or explicit time integration, right? And there is also some funny techniques in the middle, like the one I discussed just last lecture, this fast mass springs, which is exactly the implicit technique, but it's not the standard way to solve the implicit Euler method. Position-based dynamics is interesting. Basically, rejects or almost rejects this traditional view of simulating dynamics, and instead introduces a new way of looking at it. Essentially, you could even say it departs from Newton's laws of motion. It's sort of conceptual. Well, so as I said, there were these two key papers, the Matthias Müller and Jos Tam. I think they both have the same idea at about the same time. And they were, of course, it's never like that, like these guys would like discover it and you would give them like Nobel Prize or something. People before had very similar ideas. There was some game, which you probably don't remember because you're too young. It's codename Hitman game. You do? I didn't play it, but I read a Gamma Sutra article about it. And they have some method for simulating dynamics which is very closely related to position-based dynamics. It's not in the full generality, but some of the ideas already appear there. So what are these key ideas? So instead of forces, position-based dynamics, and I lump all these techniques just as position-based dynamics just to give it some label. So instead of forces, they deal with constraints. And I've explained a little bit what constraints are. Constraints are a little bit like energy potentials, but not exactly. And instead of time integration, what we'll be doing there, we'll be doing constraint projection. That will be the key part there. That's how we'll be dealing with internal forces or internal behavior of the system. Okay, so the setup is relatively standard. So you put there some mass points, just like we were doing with mass spring systems. So every point has some mass, mi, position, that's a 3D vector, and velocity, so it's a 3D vector, that's pretty standard. And then we have a set of constraints. So the most boring constraints you might expect is the spring constraint. Maybe it's more boring because you already know pretty much everything about the spring, the standard Euclidean spring. The thing is that many other type of constraints can be formulated in exactly the same framework. So for example, when we'll be dealing with cloth, we can directly define a bending type of constraint, which turns out to be fairly useful for cloth simulation. These these characters that were being tortured in the video, they were subject to volume preservation constraints. So there was some sort of simulation of a pressure inside a character, and the pressure was trying to be kept constant, subject to torturing these animals or characters. So the constraints are general, but The distance constraint, or the spring constraint, is called distance constraint in the PBD framework too. And the main difference is how we are actually doing the time stepping. So the setup of that system is fairly similar to a standard mass spring system. So let's take a look at the constraints. So what is in full generality a constraint? I said that the distance constraint is just one example of a constraint. So what is a constraint in general? So in general, we have a bunch of constraints, obviously. We have one system, and there is lots of constraints which it's subjected to. So constraint can have arbitrary cardinality. That basically means how many particles does it affect. It can really be from one to all of the particles, right? So one example, another simple example of a constraint is a position constraint, when I just say this point needs to be there, and I really prescribe the position of the target position of the constraint. You can also look at it as a spring with 0 rest length and specifically specify one of the endpoints. That's a position constraint. So for example, position constraints are, for example, used if you are doing like a character and you have some clothing on a character, like a skirt. So you typically position constrain it to the waist so it does stay there, so it doesn't fall down. And the constraint is a function, it's a scalar function from the degrees of freedom. So those are the individual x, y, z coordinates of all the particles the constraint involves, and assigns it a value, a scalar value. It's not the same as energy because this function can easily be negative. So energy could not be negative, right? But constraints are. This is just like a technical matter. Those are the indices of the particles the constraint is affecting. The stiffness parameter is just some sort of weight. It's sort of similar to like a stiffness of a spring, as you know from Hooke's law. But again, it's not exactly the same. It behaves quite differently. And also, this is an interesting thing, the final point, that we can support both equality and inequality constraints. So what does it mean? Equality constraint means that this function, the constraint function, wants to be 0. Inequality means that there is, so sometimes this is called bilateral because you could write it as both this, and this is sometimes called unilateral constraint because there is just like one of the inequalities being active. So this type of inequality constraint is useful mainly for simulating collisions. And as I said, the stiffness parameter defines the strength of the constraint. And you can already see the one obvious difference. Instead of going from 0 to some arbitrarily large number, as in Hooke's law, here it goes just from 0 to 1, the stiffness of the constraint. Okay, so the cool thing about PBD is that this is basically it. This is the main algorithm. So here we sort of don't have to like hand wave with sort of like time discretization and integrations and also the Euler techniques. Instead, it's a sequence of fairly simple operations. It starts with some initialization, and there are some. Oh, let me go through all these steps one by one. So this first three, this is just some initialization, right? We just set there some initial conditions for the positions, the velocities. Oh, and this Wi, remember this notation, Mi is the mass of particle number I, and Wi is the inverse mass. Do you know why do we prefer to store the inverse mass rather than the mass? Why do I bother like with another symbol there? Why don't I just say, well, we have Mi, so 1 over Mi.
You need to calculate the acceleration.
Correct. Yeah, that's one reason. Maybe in some architectures today it doesn't matter so much. Like back in the day, computer scientists were like crazy about optimizing number multiplications and divisions. Like your generation, I feel really old. You guys don't have to care about it so much because currently the bottlenecks are memory access, right? Data, communication, the bandwidth there. So that's Sure, maybe, but the main reason is that sometimes it's useful to have particles with infinite mass. Because if something has infinite mass, it can't move, right? Having infinite mass is basically equivalent to saying no matter how much force pushes at it, it's not gonna go anywhere. And having infinity is a little bit funny number, right? You cannot really compute with it normally. But if I represent the masses using the W instead of using the M, that infinite M is simply 0W, right? So that's simple. So that's, I think that's the main reason. And, huh?
Also it has zero mass.
What is a zero mass thing?
Like, but for some weird reason, if someone wants just to have no mass, so it's like.
Yeah, I guess so. You can pick one or the other, right? If you really, the point probably is that you usually don't need anything with zero mass. I'm not sure what would that mean really. What would it be good for?
A photon.
Huh?
A photon. Like light photon.
Right, but then you are not in physics-based animation, right? You are in rendering or physics.
Just like.
Sure. I mean, you can even store both of them, right? And choose whatever you want. No, this is a minor point. It's not much point in digging deeper into that. The point is that you can choose between representing either mi or the inverse of mi. Of course, it's trivial to convert from one and the other. And my advice is that you will probably be more frequently encountering infinite masses rather than zero masses. Both are sort of singular cases, so you need to pick one or the other. So this is the choice made in PBD and many other simulators. All right, so that was the initialization, and the interesting thing happens here. So this is the main simulation loop. This was just the initial conditions. So what's the first step? The first step is taking into account external forces. So the external forces are usually just gravity in PBD. There could be other external forces like collisions and contacts, but these we handle using constraints. So this F external here, it's almost always just gravity. And the way it works, this is just, what is this? This is explicit Euler step for integrating the external forces into velocities, right? So x is the position, v is the velocity, and this is changing the velocity based on the external force. Delta t is the time step I'm doing, w is the inverse mass. So that's gravity, that's simple. The step number 6 is damping of velocities. If things are exploding, you want to damp the velocities a little bit. I don't want to go into too much details there. Like what it can be as simple as saying that like the new velocity is the old velocity if it's like a vector times 0.99. That basically means slow down all motion. I think Tintin mentioned this a little bit, right? That's the stupidest damping, but it already works pretty well. And there are some smarter dampings which you can investigate, but usually this one is fairly good. Now the more important things are coming next. So what is the step 7? So the step 7 is an explicit forward Euler on positions. It updates the positions using the current velocities, right? So this basically, again, rings a bell. This is the Newton's first law once again, right? This is how the body, how the particles would move if there were no other forces acting on the system. You would have to like forget about this force for the Newton's first law to really apply. But this is the, so maybe a better way to say this is a purely inertial term. Another way, and more PBD type of way to look at it, is that the PIs are sort of proposed target positions of the particles. So this is like my sort of like candidate set of particles. I sort of like guess it, and then I will be improving it. Does that make sense? Step 8, it deals with collisions, so we can skip it for now. This is how do we deal with collisions in position-based dynamics. So let's not worry about it yet, and we will come back to that later. And what is really important are the steps 9 to 11. So this is the constraint projection loop, and it's a subloop of the main simulation loop. So this whole thing is usually repeated several times. The number of times this is repeated is another parameter of PBD. And here is where the main solver of PBD happens. Here is basically the substitute for integrating internal forces in classical physics. So instead of that, PBD projects constraints. Basically, the constraints are measuring how some points are how the constraints are not satisfied, and this project constraints takes the constraints one by one and projects them. Actually, I will go into that with more detail in a little bit. And the finals, this looks sort of innocent, but it's very important. These 4 lines. This project constraints is operating on the positions. I think that's why it's called position-based dynamics, right? So the PIs, those are positions of the particles. So what did I do? I moved the particles here with the velocities, right? Now they are somewhere, but I completely ignored the internal structure of the mechanism, right? So the project constraints rectifies that, moves the points around, and I end up with different particle positions, P1 to Pn, when n is the number of particles there. Now here, this is saying that I need to recompute the velocity after I have done this step, because this step that moves the particles around, so to have valid velocities in the next loop of this cycle, I need to recompute them based on what PIs I ended up with after the constraint projection loop, this loop. And this line number 14 is just saying that the final particle positions PI, I commit them to the current state, xi. That's also what I would render. That's the current state of my system. It also will be the initialization here, right? That's what I'm starting with at the next step. This velocity update is used just to deliver effects like friction or bouncing, restitution. If you want to do some bouncy collisions, you can do this here. For the first exposition to PBD, you can ignore it. So the key steps in PBD, which I would like to now explain a little bit better, are these highlighted ones. Yeah, it came out pretty well, right? And these grayed out ones, they are basically just indicating where the advanced effects would be plugged in to the solver. So I find it sort of cool that like this algorithm can just write fairly simple using pseudocode, and really the implementation of this is fairly simple. By the way, if you forget about this, if you do something else about the velocities, I did it once when I was implementing it back at Disney, and it looks really weird. You can try that when you will be doing your next homework. Oh, I know you need to first finish your Jello, but this is gonna be your next homework. So the constraint projection loop, that's the main part of PBD, right? That's why it actually does something that looks like dynamics. So let's take a look at the constraint projection step. And I will illustrate it on the most cliche, but also maybe most important example on the distance constraint, which is almost the same as a spring. So it operates on some proposed solution, on some state of the system. So this thing is always the same, right? I have some particles which have x, y, z coordinates, and that's my current state of the system. And the distance constraint, what does it do? It measures distance between some 2 particles minus their rest distance. So you can see this really the same idea as standard spring, right? Now notice that this is not exactly energy, right? How would I get energy from this? Why is it not energy? Is this because it can be negative, right? It's not very far away from the Hooke's law energy potential. Yeah, all I would need to do, if I wanted to get energy, I would just have to take the constraint and square it and possibly multiply it with some stiffness coefficient or something like that. And this would give me something like energy. It's a nice thing that PBD operates directly on these constraints. You never have to form the energy. You never have to square it. If you know something about numerics, you know that you should avoid squaring things as much as possible for numerical reasons. So how the constraint projection works. So the idea is that I set up a system which has some particles and some constraints. And then during constraint projection, I'm trying to satisfy all the constraints approximately. I cannot solve them or satisfy them all exactly, right? What would it mean if I satisfied all constraints exactly? So imagine I had like some piece of something, some piece of cloth, and I defined the constraints corresponding to like edges, just like you would set up a mouse spring system. So if I satisfied all the constraints exactly, what would that mean? It's good to realize that. Yep.
Nothing will move. Nothing will move.
That's basically true. Nothing would move. It could move rigidly, right? It could still move as a rigid body. But chances are that's not what you want, right? If you are doing rigid body simulation, that's what we'll be discussing later, and there are much simpler, specialized simulation techniques for rigid bodies. So here, and that's sort of the funky thing about position-based dynamics, is that you don't really want to solve the constraints exactly. You want to sort of solve them approximately. They can't be violated too much. If they are violated, then the constraints wouldn't have to be there. So they sort of like have to be close to zero. You can write something like this: that Pi Pj should be approximately zero. So one way you could do it, you could set it up as a system of nonlinear equations. You could put all the constraints together, and then basically do something like Newton's method. Linearize all the constraints. By the way, the constraints are again nonlinear, right? In Newton-Raphson method or Newton method, that's the same, by the way. Don't find there any difference. What is the problem of that? The problem is that at the current state, this is the current state, Newton's method establishes a global linearization. We take the entire system, we look at the entire system as one vector living in some high dimensional vector space, and we take all the constraints all together, and we do a global linearization of the entire system. Okay? That's why we also then need to solve linear systems, which put all these things together. Now PBD, and that's a very important idea of PBD. I'd like you to remember this. PBD does not do that. It does not do the global linearization, and it does not do any global linear system solves, which is also why it's much easier to implement. You don't have to worry about any linear system solvers. So what does it do instead is it linearizes the constraints one by one. So one constraint is linearized, projected, and the state is updated, and then I move on to another constraint. And I again project it, like make it better satisfied, update the state, and move to another constraint. I think that's also the reason why PBD gets away only with first derivatives, so you don't need second order derivatives, you don't have to worry about any Hessians, which is another very, very nice thing. Like, you know now that computing Hessian is not always fun. So it's better to deal just with gradients, and that's what you do in PBD. So here again, that's the main idea of PBD. The constraints are projected one by one, and essentially you do one distance step per constraint locally. So if you were doing like a cloth, it would be projecting every single distance constraint at a time. So this could be interpreted as a nonlinear version of Gauss-Seidel iteration, right? You should know the Gauss-Seidel method for solving linear systems. How does the Gauss-Seidel method works? Somebody remembers that? You have a system of linear equations, right? And you want to solve them. How does Gauss-Seidel solve it? Gauss-Seidel is one of the simplest methods for solving linear equations. Anybody? Okay, it's probably so simple that you'll be embarrassed speaking it out loud. You just take the equations one by one. You take the first equation and you solve it, right? You make it satisfy. Then you move on to the second equation, solve it, and so on. And then you do sweeps through the entire system. That's the idea in a nutshell. Now, PBD does not have linear equations. It works with nonlinear constraints. That's pretty much always the case in physics, as we already discussed before. But the key insight why this works better than the Newton's method is that we are immediately committing the updates to the state. So as we project one constraint, it immediately affects the state, and we go on to another constraint at already the updated state. So the next linearization works already with the updated state. So let's take a look how the math exactly works. Then it will probably be making, hopefully, more sense. So here is some constraint function. The P is here the aggregated state. So I guess I could write the P like this. P1, it's the first particle up to Pn, like one big vector. And the delta P is the displacement. That's I change it just a little bit. Using Taylor approximation, Taylor expansion, you can write it like this, right? This is our favorite operator, the gradient, in respect to P, of course, and this is the displacement. So don't confuse these symbols. This just means like a displacement in P. I could have also used a different symbol there. I'm just trying to use the same notation as the original paper, so you have an easier time reading the PBD paper. And this is basically just gradient descent. So we want to choose the delta P such that the P plus delta P gets us closer to 0, gets the constraint closer to 0. So the way we do it, we go in the direction of the gradient at the current state, and we march by some length lambda. That's the step size. So if we compute, then we can directly compute what the lambda should be so that this equation is satisfied. So let's see. So if we decide that our delta P, our displacement of positions, is going to be lambda times the gradient, then what we can do, we can just substitute this back here, right? So if I have this equation here, I can just substitute this here, and I get Cp plus lambda times, now this is a dot product, so I'm doing dot product of the gradient with itself, so it's going to be squared norm of the gradient. This is a gradient P Cp squared, and this should be 0. So all I did, I plugged in for delta P this expression here. Okay, and now I can solve for the lambda, and what I get is that lambda must be minus Cp divided by the squared norm of the gradient. Yep, everybody happy about that? Sort of makes sense, right? And then I can just plug the lambda back here, and this is what it gives me. So this is the minus Cp is here. This is the divided by, I sort of prefer the double thing for norm the gradient. This is the norm of the gradient squared, and this is the direction of the gradient itself. So this is the optimal update. Now I need to refine this idea a little bit, because we need to take into account individual masses of the particles. If all the particles had the same masses, this would basically be sufficient, but sometimes we want to deal with particles with different masses, sometimes 0, sometimes even infinite, right? But most frequently they will be somewhere between 0 and infinite. So let me write the same formulas with a little bit different notation. And I'm sorry, the notation is not ideal, but that's what it was in the original paper, so I just stick with that notation rather than trying to improve on that. So here is the same idea, but now written per particle. So this is a displacement of particle number I going from 1 to n. Now what previously was lambda is now denoted as minus s, which is the weird notation, but that's just a notation, whatever. And here is the gradient of my constraint. I can also be denoting this just by P, so I don't have to write P1 to Pn. The important thing is that the gradient is just with respect to the ith particle number I. And this is nothing but this formula. The minus here, it's just an extra minus because, as I said, minus s is what lambda was here. But other than that, this is the same. This is just the square norm of the gradient written using the individual particles. Now, the important property we need is translation invariance of the constraints, because from this will follow conservation of linear momentum. So that's an important point about the constraints. The constraints are there, at least these type of constraints are there to simulate the internal, or sort of sidestep the internal forces in the system. And the internal forces of the system have the property they cannot really change the center of mass, right? If you have some elastic object or any type of object really, and the object by its internal actions cannot start moving itself, right? If I have, like, no matter how strong springs I have in my elastic object, if I just compress it and let it go, it cannot just like fly away somewhere. There must be some external forces acting to make it change its center of mass. So what we need from the constraints is to conserve linear momentum, and the same thing also for angular momentum. And in the case of all particles having identical masses, or having masses 1, that's basically what this case corresponds to, then this is all we need. Now, if we want general masses, then we need to change the constraint projection a little bit. So this is for the case, this works for the case if all particles have exactly the same mass. And if the particles have a different mass, if particles have individual masses, then the conservation of linear momentum is this, right? We take the displacements of the individual particles, we weight them by the masses, and if the system is not to change its center of mass, then this must be true, right? The displacements times the masses must be 0 when I sum all of them together. Now, to make sure this is true, assuming the constraint has the translation invariance property, then I need to change my update by scaling it by the inverse mass. So I guess here is your reason why you would want to be storing 1 over mi to save the division here. If that's important. Well, most likely that's not important. So this is basically like we were doing before, right? The only difference is, so this is what we were doing before, minus s times the gradient, and this is the same thing except that there is the wi, right? So why do we put the wi there? Well, that's because if I now plug this back here, what happens? What happens is that the mi, wi, that's of course 1, right? So that cancels. So if I plug it in, I get, sorry, no, mi. I guess minus s, sum of the gradient with respect to pi of my constraint p. And from this property, I know this is 0, which means that the weighted sum is 0. Which means that it conserves the center of mass even though the particles have different individual masses. Okay? Let's see. So this is this update, and this coefficient by how much do we want to move in the direction of the gradient of the constraint. That's this s variable that changes by adding these w's into the denominator. So let's see how I could explain this nicely. So what we want to do, so let's see. So we want to find the deltas this is my gradient, pi, this is C, P transpose, and I want to find these delta pi's. Okay, so this should be 0. Okay, this is my current value of the constraint, this is the gradient. I just prefer to denote the dot product, so this is a dot product between the gradient and the displacement. I just prefer to denote it with the transposition. You can also denote with the dot. And if the delta pi's are this, are the minus S Wi. Well, let me try to plug it in there just to explain you where this equation came from. So if you plug it in there, I will get here minus S sum Ri Wi, and what I get here, this is the gradient, and this is also the gradient. So this is just dot producted. So this is the norm squared of the gradient, right, which needs to be 0. And from this, I will see that the S is nothing but, I guess that's the reason for the minus there, so that the minus disappears here, because this is what I will get. Iwi times the norm, the gradient, Cp. I'll give it 2 bars for. So here, this is where it came from, basically. I just said that the updates of pi will not be the same for all particles, but I will weight it by the inverse masses Wi. So this is the weighted formula there. So this might be a little too abstract because we are looking at constraints in general. So let me make it a little bit more concrete by looking at the distance constraint, which is similar to our well-known spring constraint. And we can get the update rules simply by plugging into these general formulas which we have just derived. So the distance constraint, it picks some 2 particles, and it says that the distance, the length of the vector between the 2 particles should be similar to d, right? This constraint is going to be an equality constraint, so I want this to be approximately equal to 0. And the point of the constraint projection step is to come up with these updates, delta P1 and delta P2, such that after I add them to P1 and P2, after I do P1 plus delta P1 and P2 plus delta P2, I get something that satisfies the constraint better, right? In this case, I can satisfy the constraint exactly. That doesn't have to be always the case. I just need to make things better. I don't always have to satisfy the constraint exactly, but if I can, that's better. So this is something you are familiar with, how to differentiate this expression. It's basically a simpler version of differentiating the spring energy. So here I'm differentiating this expression. Again, always keep in mind P1, P2 are R3 vectors, right? X, Y, Z coordinates of the particles. So this is the gradient of this expression with respect to P1. And it turns out it's a unit vector which points in the direction of the P1 minus P2. If I compute the gradient with respect to P2, it's just minus n. It should not be a surprise because I know that these 2 things must sum to 0, because this is a translation invariant constraint, right? If I have like a spring like this, I translate the entire thing, the value of the constraint is not going to change, obviously, right? If I add t to both P1 and P2, I'm not changing the value of the constraint. Okay. So what was this S, the coefficient I derived right here? So the coefficient S was the constraint value divided by the sum of the inverse masses times the square norm of the gradient, right? So in this case, it's simple because the length of n, what is the length of n? 1, right? So in this case, this goes away. This is just 1, right? And I have just 2 p's here, p1 and p2. So this is just w1 plus w2, right? And this is the value of the constraint. In this case, the constraint is the norm of p1 minus p2 minus d. So this is what I have here. So this is exactly this form applied to the specific type of constraint. All right? And here, what I have down here is this is the general form for the displacement. So I take this s, I multiply it by wi and the gradient. So if I do that here, so what is my s? My s is this, p1 minus p2 minus d divided by w1 plus w2. So this is my s, this thing here. Here I multiplied by wi, just like this formula dictates, right? There's this minus here, that's this minus here. And where did this come from? That's the gradient. The gradient is the normalized p1 minus p2 vector, so that's exactly what's here. Okay? The only difference with p2 is the sign. It goes the other way, and it's also weighted by w2. So that's quite simple, right? Because geometrically, all that means is if I have a distance constraint, if I have 2 particles connected by a distance constraint, then what the constraint projection does, it measures the current length, or computes the current length, right? That would be the p1 minus p2. And then computes the displacements delta p1 and delta p2 such that after doing p1 plus delta p1, so that's this, right? This is p1 plus delta p1, and here, of course, it's p2 plus delta p2. So the distance between these 2 points is now exactly d, which means that the value of the constraint at this new state is exactly 0. The constraint is exactly satisfied. Just like Gauss-Seidel, right? It exactly satisfies one of the equations. You can clearly see what is the problem with this, right? By satisfying one of the springs, there are many other springs, right? Which might be now even more violated than they were before. So that's why I have all these loops there, that I have to loop through all these springs and do this constraint projection, or distance constraints, and then do the constraint projection for every single one of them. And then loop it a couple times so it sort of equalizes. Okay, what else? Here is, the intuition about these weights. You can see that if the W1 and W2, if they were the same, if both the points have the same masses, then this is just 1/2, right? So that's really the simplest case. If both of these particles have the same mass, then it means that this delta P1 has the same magnitude as delta P2. Both are moved equally, right? And of course, if one of them has high mass, so for example, if P1 has large mass, it's a heavy particle, and this is a light particle. So if M1 is large, that it means that W1 is going to be small, and that means that delta P1 is going to be small, right? So intuitively, the large guy is not going to move a lot, and the lighter guy is going to take all the motion. Which sort of makes sense, right? So that's the distance constraint, which is really the key constraint in PBD. That's all these results we were looking at were using the distance constraint. And we can look at some other type of constraints. If it was just the distance constraint, you would be like, yeah, whatever, I can do it with Hooke's law, right? But there are some more interesting types of constraints. One of them is the bending one, which is useful for cloth and thin shells. You know what's the difference between cloth and thin shells? Thin shells can be things that don't have to have flat state, right? Like all these cloth, they are developable surfaces. They can be put on the plane because that's how the cloth started with to begin with, right? There was like a sheet of textile which you sewed together. Thin shells, they don't have to be developable. They can have arbitrarily rest shape. So imagine something like a hat or a soda can, something that's curved at the rest shape. So with this type of bending constraints, we can simulate both, which is sort of nice. So the simplest thing we could do, the alternative thing we could do, and I think that's what we mentioned before in mass spring system, would be cross springs, right? What are cross springs? If I have one triangle here and another triangle here, then I can simply put a spring right here, right? And this spring will make it resist bending, right? If this is like a hinge, oh, I don't know if this works. If it's like a hinge thing, then this spring will certainly resist bending. The problem is that also interferes with in-plane stretching, right? If I put the spring there, it's not only resisting bending, it's also resisting stretching in that direction. And maybe that's not what I wanted. And also it gets trickier if I don't have completely flat rest pose. Then the cross spring might not work ideally. So what we can do in PBD is a bending constraint, which looks like this. Because the constraints, they can be really arbitrary functions, right? Nonlinear, whatever you come up with, that can be a constraint. It should be translation, rotation, and variance, so we are not modifying the linear and angular momenta. But that will be the case here. So if I have a hinge like this, two triangles connected by an edge, what I can do, I can compute the normal of one of them, normal of the other one, and I put it in this convention, so this one like goes up, this one goes down. So if I look at it from the side, this is like the side view, this is the normal of the first triangle, the normal of the second triangle, which points down. And I just measure the angle between the two normals. So this is really computing the angle of the hinge, essentially. And this is, here is the formula. So this is really nothing that, I mean, it looks scary, but there is really nothing special going on there. So what happens is that I decide that the P1 is going to be my point of reference, and I just do P2 minus P1, that's this vector, right? P3 minus P1, and I do their cross product, and I normalize it. And that gives me the first normal vector. Same thing here, right? Except that here I do P2 and P4. Oh, yeah. P2 and P4 cross-producted. So this gives me the vectors n1 and n2. So this is the n1 and n2. I take their dot product. They are unit, that's why I normalized it here. And by taking the arcus cosine, I get the angle between the two vectors, right? So the way I chose the orientations is that flat configuration corresponds to 180 degrees, and a completely bent thing, like the hinge completely bent over itself, like double sheet on the same triangle, that would register as 0 degrees. And the thin shells I can fairly easily support by subtracting the rest pose bend angle as phi 0. So normally you would probably want there 180, but you can put there something else if you want to do something shells. That's the bending constraint. Sort of slightly tricky to compute the derivatives. I'm not gonna torture you by computing the derivatives of this. It's even trickier to do it like numerically, right? Because there are some corner cases you don't want to divide by 0, right? Arcus cosine is also not defined everywhere. Even Matthias told me that they are not using it much, this type of bending constraints. Nevertheless, it's possible to get it working. I eventually got it to work, and then it works fairly nicely. Now, even more funny constraint is the pressure constraint. It's funny in a number of ways. And the one funny is that it's been used for this like pressurized character, which is then like put through gears or things like that. And that's what makes it maintain the volume. So you can look at it either as preserve the volume of the object, or physically you could look at it as like a pressurized balloon type of thing. That the character is sort of like hollow, that there is nothing inside, right? That's what all computer graphics things. They're just like surface and nothing inside. But that nothing inside you could interpret as some air, which is some pressure. So it resists change of the volume, if you wanted to give it some physical interpretation. Do you know this formula for computing volume of a mesh? Do you know the 2D version of this? If I have, so the easy case is a convex polygon, right? If I have some convex polygon and I have the orientation of the edges like this. Oops. Do you know how I compute the area? It's like, this is like a 2D analog of this. This is a 3D version, this is a 2D version. So the 2D version is easier to think about. Do you know the formula for this? It's called the shoelace formula, I believe. So the idea is you pick some point there and you compute the areas of all these triangles, right? If you sum them together, you get the area of the entire polygon. Now, interestingly enough, this works no matter which reference point you pick there. So if I pick the reference point like here, and I correctly take into account the orientation of these edges, that's very important there. So this would be like negative orientation triangle. This would be positive. So as I'm summing it together, that basically means erase this area and add this area, right? Same thing with this triangle. This triangle kills this area and adds this area. So at the end, I again end up with the correct area. This is the same idea in 3D. This is just an intuition. Of course, this can be derived precisely mathematically from the divergence theorem. But again, I don't want to go too deep into this. This is just like another type of constraint. The cool thing about this constraint is that that's a constraint which constrains all the particles of my object at the same time. So it's very different from like springs or distance constraints, right? The distance constraint, they were only looking at 2 particles at a time. I can have thousands of particles. This one is looking at all particles at the same time. Another very useful and very simple type of constraint, though a little bit special, is the point constraint. As I said, that's just a constraint where you directly specify the target position of the particle, where it wants to be. The white is a special case. This, of course, does not conserve momentum because you are specifying a target position of that particle. So it's more really like external force if you think about it. But it's fine. All you need to know is that this really does not describe an internal process in the object. It really means that there is something else affecting the system. So the typical example, if I'm doing like a skirt on a character, I put there like one row of position constraints by the waist, and that makes sure that the skirt is not going to fall off. Right? You could do it with friction and those things, but then you are not guaranteed it's actually not going to fall down, and usually you want to guarantee that. Point constraints, they will guarantee it's not going anywhere. And it's very simple. Also, if you have a point constraints particles, and that's why you would want infinite masses, if the point constraint particles, you give them mass infinity, that way you will make sure that there is no gravity and no such things acting on it. Because nothing can beat the position, or point position or point constraint. Some people call it position constraint, some people call it point constraint. Doesn't matter. The point is that if there is a point constraint on a particle, that means directly specifying its position. So it doesn't matter what inertia it has, it doesn't matter what gravity acts on it, right? So you can say, okay, the mass is infinity, and all the equations will automatically do nothing to it. Now the only problem is if you have 2 particles which both have infinite mass and they are connected by a distance constraint, you need to be a little bit careful in the code not to divide by zeros in that case. All right, how to do the collisions. So I promised you to explain where to stick in the collisions. You might be dealing with collisions right now on your Jello thing, right? The idea in PBD is fairly similar. sort of the basic type of collision. So what do we do about collisions? We first detect them. Detecting collisions is a topic for itself, so we will have probably a lecture by itself for collision detection. If you are detecting collisions with some simpler shapes like half spaces with a plane or a sphere, that's simple, right? That's what you are doing for Jello. So in this case, the generate collision constraints become simple. If it's detecting collisions with a general object, then it's a little bit more tricky. Nevertheless, let's assume that this routine generated contact points or already penetrated points for us. And the way PBD handles the collisions is that the collisions generate special type of constraints called collision constraints. So this is what I just said. Basically, let's assume you have already detected them, which is really simple for simple objects. And then we set up this collision response constraints. The interesting thing about the collision constraints is that unlike pretty much all the other constraints, unlike the distance constraints and pressure constraints and bending constraints, the collision constraints, they change every step naturally, right? Because every step it's colliding at a little bit different particles usually. So how do the collision constraints work? So if I assume this is some collider here, like an ellipse, and here is where I started. Here is where my particle was at the previous step, so everything was fine. But in the next step, somehow it made its way inside the collider. So that's not right. It should not really be there, right? So the simplest thing I can do is just connect this with line and find where it intersects the collider. So that's the last valid point of that particle. If I sort of imagine the particle traveled along this line, right? Then what I can do is find the normal of the collider at this point. I'll call it NC. And the normal defines a tangent plane. So this is a tangent plane. And this tangent plane in turn defines a half space of allowed positions of vertex P. So this is saying that the vertex or this particular particle is not allowed to be here. It is allowed to be here, right? So mathematically, I can express it by computing the dot product of P minus QC times the normal, and I want this to be positive. This is an equation of this half space where it's okay for the particle P to be, right? You can see, of course, it's not exact, right? It's just like, again, linearization of the contact point. Correctly, I should say that the particle is allowed to be anywhere in the region outside of the collider, but the point is that I'm doing only small steps, so I can get away with just this linearization. And in the next step, if it's still colliding, then I do this thing again, because then it moved somewhere else, then I will have a different linear approximation. So here is this thing summarized once again. So this is a collision constraint. Again, it's a constraint just like any other constraint. The only difference is that now this is the unilateral constraint, the inequality constraint. So I'm not looking to satisfy to put it to 0, but I only want to do something when this CP is negative. So how do I handle unilateral constraints in the constraint projection loop? Well, I check if they are violated, right? That means if CP is negative, and if they are violated, then I project them. If they are not violated, I do nothing. They are fine.
Sure.
Mm-hmm.
For the left side, it's not shaping into convex. I mean, if it is concave, so you need to use the normal.
Yep, you are absolutely right. This does not have to work always. I guess the disclaimer here, this works only if you are taking sufficiently small steps and the concavities are not going to kill you. So indeed, this is like the simplest approach to collisions. Yeah, but most of the time it's not that bad, because even if you like, yeah, this is what you were saying, right? If I have a collider which looks like this, right? And like my particle goes here, so this and here is like a collision constraint established, so I'm perfectly fine to go there, right? It's usually not the end of the world, because then there is the collision response would be invoked again, right? And I would be pushing it out from there too. And by the way, this whole thing is part of the collision of the constraint projection loop, right? So if I give it more iterations, I have a better chance of actually resolving it and ending at a valid state. There is no guarantees that you will always end in a valid state, right? Very, very little guarantees some days. Yeah, the collisions, they get pretty tricky, especially with not convex objects. All right, so this is one more, the entire PBD algorithm. I wanted to spend a little bit on discussing the pros and cons of position-based dynamics. Why should we be doing PBD compared to the standard approach to simulating dynamics using, for example, implicit Euler or even explicit Euler? So what are the pros and cons? I think the advantages are fairly obvious, right? PBD is easier to implement. It requires only first order derivatives and only local, only per constraint. So that's quite easy to compute. What are the disadvantages of PBD? There's quite a lot of them actually. Another advantage is that it's fast. Fast in terms of computing performance. In terms of convergence, not so fast. This is what I will discuss in a second. There are some improvements to make the convergence speed faster. Other problems are with the coefficients, with the parameters. The stiffness parameters k, the stiffnesses of individual constraints, they are not compatible with like the standard physics-based parameters like the Hooke's law. Even more importantly, the resulting stiffness of the material depends not just on these parameters, but also on the number of iterations, of this loop, right? This loop is repeated for some number of iterations. Could be 10, could be 50, could be whatever you said. It could be also 1, but then it usually looks fairly funny, too stretchy. And the more iterations you give it, the more stiff the system will be. The stiffness also depends on the time step, on the delta t. So if you change that, then you basically need to change pretty much all your coefficients. So that's slight disadvantage of PBD. Another problem is that if you are increasing the solve iterations more and more, if you are giving it more and more iterations, it may not be getting better and better, because as you correctly pointed out, it converges to rigid body motion of that object, right? So it's not like the previous technique, our fast simulation of mass spring systems, which converges to the exact implicit Euler solution. This converges to exact rigid body motion, which if you are doing something like Claude, that's most likely not what you are after. Yeah, those are the disadvantages of PBD. Nevertheless, the advantages are pretty strong, and that's why PBD is used quite a lot, both in games and film. I think it's continued to be used in Maya. Solver 2 is definitely used in physics. They also had a paper just last year at SIGGRAPH about position-based fluids. So the same idea has been generalized to fluid simulation. Again, with pretty much the similar advantages, look pretty good. So the one problem I mentioned just briefly is the slow convergence. So what happens, maybe let me ask you this way. This is like the answer, so let me go back to the question. The question is, what if I don't do a whole lot of solver iterations here? What if I do just a few solver iterations? What if I repeat this loop just like once or twice or 3 times? It's not going to explode, interestingly. this thing is very stable. It's not that it could not explode, but it's pretty hard to get it explode. We tried. So what do you think happens? Well, the answer was there. So if you are doing something like cloth, it just becomes too stretchy. So it essentially gives up on the material properties it compromises the material properties to guarantee stability. If you were simulating some stiff system, Euler would basically explode. This does not explode, but instead compromises on the stiffness. So instead of some sort of cloth, like normal cloth, which resists stretching quite a lot, PBD gives you some very stretchy cloth. And that's because Gauss-Seidel is not really the most efficient numerical technique in terms of convergence speed, right? If you think about it, it sort of makes sense. If you think about how the information propagates. So let's, again, if I have like a sheet of cloth like this, right, with like lots of particles, like this, and let's say it's like hanging on the two corners. Those are the test cases we were using with Tintin, right? So if you move one of the corners somewhere, if I just like I'm hanging a piece of cloth, I move one of the corners, right? So that means this would be position constrained particles. Here will be distance constraints between all the other particles. And what happens if I move this position constraint somewhere else? If I apply basically external force to this? The result depends on the ordering of the constraints in the constraint projection loop, right? So here I'm saying project constraints, all of them one by one, and this order actually matters, right? If I pick a bad order, if I go always like from here, and go through the particles like this, I do sweeps like this, and this is gonna be the last one or almost last I hit, right? So if I just move this point here, all these constraints are going to be perfectly satisfied. They're going to be doing nothing, right? The only change happens after I get to this region where the external forces were acting. So this you can trivially see this is very wasteful, right? Because the way information travels across the mesh, I have to do a sweep across all the constraints in my system to do just like a little bit of useful work. This sort of, you might think that some sort of reordering of the constraints might work better. And I have seen some game papers that do something like that, but it only works in special situations. Like if you have something very simple like a rope, so basically just a chain of constraints. So those are particle joined by distance constraints. And if I know that only this one is position constrained, so of course if I move this, then the order I want to traverse the constraints is like this, right? I want to go to this one first, this one second, this one third, fourth, and fifth, right? But this would be different if this one was free and this one was position constrained, right? Then the order would change immediately. For chain, it's simple. For something like this, it's more difficult. And if there are collisions, then it's impossible to come up with a fixed ordering that would be always good, right? Because you don't really know where you're going to poke it with some collider. And if you try changing the order in runtime, it can also look pretty funny. The solver, it looks really weird. It almost looks like the momentum was not conserved or something like that. One possibility, which Matthias introduced later, is to do hierarchical PBD, use a multi-resolution acceleration. It's a similar idea to as coarse to fine multigrid. Basically do the PBD first on a coarser version of my system. It's like great, but it could be like whatever system of constraints. After I've done it on the coarse version, then I upsample it to a finer scale version and then do constraint projection on the finer scale version. I can show you the video if you still have a few minutes, right? I can show the improvement. This will also nicely show you the stretchiness of the cloth. There, hierarchical PBD. It's time for a video anyway. So what you have on the right. Which one is which? Yeah, this is standard PBD. If you don't give it enough iterations, then the club becomes really stretchy. See? And as you increase the number of iterations, it's getting stiffer and stiffer. But of course, it costs more and more, right? Because the iteration means sweep through all the constraints, which is slow. So instead, the hierarchical PBD, it only takes 2 iterations and it's faster. Here you can see the levels, of course, are defined going. The finest level. And you can do either irregular or regular discretizations. Sort of cool that you can still be tiering it, because then you have to update all the levels of the hierarchy. Tiering is a cool effect, and it's not even that difficult. You might even try it for your next homework. It's called if the stretch of a triangle or even the distance constraint exceeds some threshold, then you just say, okay, broke now, remove it, and continue simulating. That's fairly funny looking simulation, but it's real time, I believe. Oh, that's weird. There are other improvements, like long-range attachments, which is much simpler than hierarchical PBD. Oh, sorry. Yeah, I wanted to finish quickly because we're gonna move on. Another improvement of PBD is this long-range attachments, which basically says that you skip in a chain. You can do, instead of having just these constraints, you basically say that even these distance guys are connected by a distance constraint. That also helps the stretchiness quite a bit. There is another paper by Matthias at C892 that does exactly that. Okay, we have to finish right here, but I will see you again on Wednesday. Okay?